Welcome to ThirdEye Labs, where we make the unseen seen. Today, exponentials and logarithms. Remember from the notation episodes, we learned to read symbols like the sum and the exponent. Now the exponent takes the starring role. Every time the exponent goes up by 1, the value is multiplied by the base. Not added to, but multiplied. After 42 doublings, starting from 1 millimeter, we reach the moon. That is the signature of an exponential. The jump gets bigger the bigger you already are. Think of a rumor. One person tells two, those two each tell two more. The crowd is not growing by a fixed count. It is doubling. That is exponential growth. Among all possible bases, one is special. E, approximately 2.718. It is the unique number where the exponential function is its own derivative. Its rate of growth at every point equals its current value. That self-referential property makes it the natural base for continuous processes, like population growth, radioactive decay, and neural network activations. Imagine a bank that compounds your interest not once a year, not once a second, but continuously. The value you end up with after 1 year is exactly E times your starting amount. That is why E is called the base of natural growth. Let us actually draw it. Here is e to the x. Now watch the slope. At every point, the steepness of the curve exactly equals its height. Where the curve is at 2, its slope is 2. Where it is at 6, its slope is 6. That is what it means for a function to be its own derivative, and it is unique to e. The logarithm just asks the inverse question. If 2 to the power 10 equals 1024, then log base 2 of 1024 asks, to what power do I raise 2 to get 1024? The answer is 10. Exponentiation and logarithm are mirror images. In machine learning, the natural logarithm, base e, appears everywhere. If a rumor reaches 1024 people, the logarithm base 2 asks, how many doublings did it take? The answer is 10. The log is the inverse of the exponential. Because the logarithm undoes the exponential, their graphs are mirror images. Reflect e to the x across the diagonal line y equals x, and you land exactly on the natural log. Every point on the yellow curve has a twin on the blue one. Input and output simply swap. Here is a deeper way to see the natural log. Take the curve 1 over x and measure the area underneath it, starting from 1. When you reach x, that shaded area is exactly the natural log of x. At x equals 1, the area is 0, and it grows more and more slowly, just like the log. Logarithms have a superpower. They convert multiplication into addition. The log of a product equals the sum of the logs. In practice, this means multiplying probabilities, which gets tiny fast, is replaced by adding log probabilities. That is exactly why machine learning uses log likelihood and cross-entropy. This superpower is exactly why logarithms were invented in the first place. In 1614, a Scottish laird named John Napier spent 20 years of his life building the very first log tables, just to turn brutal multiplication into easy addition. Astronomers said it doubled their working lifespan. The slide rule that ran on his idea then powered 3 centuries of engineering, all the way to the Apollo moon landings. Not bad for a 400-year-old shortcut. A slide rule is a physical log table. You multiply 2 numbers by sliding a ruler, and you are literally adding logs. This trick powered every calculation before computers. When you plot training loss over thousands of steps on a linear axis, the early drops dominate and later progress looks flat. Switch to a log axis, and the curve straightens. Every halving of the loss looks the same size. A straight line on a log axis means exponential decay in the original data. That is the standard way to plot loss in every deep learning paper. A world map fits continents and cities on one page by squishing distances logarithmically. A log-scale loss plot does the same. It fits 0.001 and 10,000 on one axis. And once you know the trick, you spot log scales all over the real world. The Richter scale for earthquakes, where a magnitude 7 is not a touch worse than a 6, it is 10 times the shaking. The decibel scale for sound. the pH scale for acidity. Each single step is a tenfold jump, squeezing an enormous range onto a tiny ruler. Exactly the same move as a log axis on a training loss curve. Finally, lift it into 3 dimensions. Slide the base upward from one, and you get a whole landscape, every exponential at once. Flat near a base of one, then curving up faster and faster. The red ridge is our special base E, sitting right inside the family. The same E that describes natural growth also shapes how neural networks output probabilities. The sigmoid function wraps e to the x in a fraction that squeezes any real number into a value between 0 and 1. Softmax generalizes this to many classes. We will build both from scratch in Season 4. For now, notice they live inside every classifier you will ever train. A very common mistake, using exponential to mean really fast. That is wrong. The defining feature of exponential growth is that the rate of change is proportional to the current value. Mathematically, the derivative of y equals k times y. A rumor doubles faster when there are more people to spread it. That self-similar feedback loop is what separates exponential from merely large. Let us recap. An exponential raises a base to a growing power. Every step multiplies. E is the natural base where growth rate equals current value. The logarithm inverts the exponential. It recovers the exponent. Logs turn products into sums, the foundation of log likelihood and cross-entropy. Log axes reveal structure hidden in explosive data. And exponentials inside Sigmoid and Softmax give every classifier its probabilities. One last thought to carry forward. Almost every neural network you will ever train has a loss that falls roughly exponentially. That is exactly why researchers plotted on a log axis, so that steady learning shows up as a clean straight line. The next time you watch a training curve bend and flatten, you will see the hidden exponential underneath it. So tell me in the comments, where else have you caught an exponential or a logarithm hiding in plain sight? Next time, how a spinning point secretly draws every wave in nature. Thanks for watching and keep exploring. Next time, trigonometry and the unit circle. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.